So, welcome back. In today's lecture, we will do the next step after finite element modeling, which is we will do the finite element discretization and we will look into the finite different discretization. That is, we will see discretization in space and discretization in time, and we will also see how the final Newton-Raphson procedure is set up, and I will just briefly mention what are the special things that you need to take account during the simulations. Okay. So, the thermal formulation and the contact formulation will keep it for the next lecture, and also some of the results that were obtained using this formulation. So, you will get an overall picture of how the concept that we have discussed in this course could be applied for simulation of a much more complicated problem. Okay. So, today we are just going to see the finite element and finite difference formulation. Okay. So, to start the finite element and finite difference formulation, okay, so we first have to derive the integral form of the equation of motion. Okay. So, you need to remember that we are doing an updated Lagrangian formulation, which means that we know everything at time t and we want to compute the state of stress and the deformation of the body at time t plus delta t. Okay. So, we know psi t and we want to know psi t plus delta t. Okay. Psi is the current configuration. Okay. Now, it is to get the integral form of equation of motion, it is given by the incremental virtual work expression at time t plus delta t. Okay. So, we use the updated Lagrangian formulation, which is developed for one body in the previous slide, and we easily extend it to two body problems. Okay. So, we will do this for single body, okay. And because we are dealing with a contact body, so you can imagine this is written for body A, and then you can write a similar expression for body B. Okay. So, you see this is the virtual work of the inertia forces at configuration t plus delta t, okay. And this is the internal virtual work at t plus delta t, okay. And these should be equal to the external forces at time t plus delta t. Okay. So, here you have density at time t plus delta t, you have the acceleration, you have the virtual incremental displacement vector at time t, okay. You have the configuration of the volume at time t plus delta t, this is the Cauchy stress at time t plus delta t, okay. And then the virtual incremental linear strain tensor can be written using following equation. Okay. So, now the external forces. Okay. So, the external forces are nothing but the external forces because of the body forces. Okay. So, the external forces because of the applied surface traction, and because we have contact problem, you will also have the external forces on each body because of the contact stresses, okay, or because of the contact traction. So, this C over here denotes the contact. Okay. So, you have two bodies. Okay. So, say you have these two bodies. So, a certain part, so you will have body forces inside the body. So, B 1, let us say B 1 and B 2, you may have applied external tractions which are other than the contact tractions, because the nature of the tractions on the surface and on the contact surface remain same, but we will distinguish between what is applied externally and what is because of the contact. And then when you separate these two bodies in contact, so this is body A and body B, at this surface each body will experience what is called the contact traction. Okay. So, this body will have a compressive traction like this, and body B will have a compressive traction like this. Okay. And in addition, if the bodies are sliding over each other and there is friction, so there will be two kind of tractions. One is the normal traction, which is because of the normal contact, and the tangential traction, which is because of the frictional force. Okay. So, you have the body forces, you have the applied surface tractions, you have the surface. Okay. So, this is the contact surface, this is the applied traction surface, this is the contact surface. Okay. So, remember this formulation we have taken from Bathe. So, there is a difference in convention in which we are write. So, initially we are writing, for example, this as B, okay, and initial surface is B0, but now it is written as T plus delta T V for body configuration at time T plus delta T. So, but anyway the idea remains same, the terminologies change, but the idea is same, which we discussed in our chapter on kinetics, where we discuss principle of virtual work. Okay. Now, the main difficulty, as we already discussed previously in using the incremental virtual work, is that we do not know the configuration at time T plus delta T. So, we cannot carry out those integration over the volume and the surfaces. Okay. So, therefore, these expressions need to be transformed to an integral over volume T, and this we can do by the pushback operations. And once we do that, okay, so here we have used one formulation which was given by Bathe. Okay. So, when you write the configuration, okay, so the integral equation over volume T plus delta T you write at time T, okay, which is here, then you get the following expression, and instead of the Cauchy stress you get what is called the second Payala-Kirchhoff stress tensor. Okay. So, remember this P we use for first Payala-Kirchhoff, but here this corresponds to the second Payala-Kirchhoff stress tensor. Okay. And the virtual Green-Lagrange strain tensor comes out at the corresponding conjugate stress measure. Okay. So, here again instead of capital E we are using this small e. Okay. Now, the incremental virtual work expression, okay, is a nonlinear expression. Okay. Now, in our previous discussion what we had done was we first did the discretization and then we did the linearization, but here we follow Bathe, and as I mentioned in my those lectures also, there is another way you can do linearization first and you can do discretization later. So, which is what Bathe follows. So, here also this current formulation what we do, we use linearization first. Okay. So, for linearization we use the following procedure. Okay. So, for first the second Payala-Kirchhoff stress tensor, okay, which is here, is decomposed as the second Payala-Kirchhoff stress tensor at time T plus the increment in the second Payala-Kirchhoff stress tensor. Okay. And the second Payala-Kirchhoff stress tensor at time T is nothing but the Cauchy stress tensor at time T plus then you have the increment. Okay. And the virtual Green-Lagrange strain tensor can be decomposed into what is called the linear part and the non-linear part, where the linear part is just like your linear strain tensor, and the non-linear part has the product of the gradient of the displacement, okay, at time T, okay, incremental displacement at time T. So, now if you substitute these expressions and those in the previous in equation 56, okay, so you will get following expression. So, you will have the inertia forces, you have delta P times the linear part plus the non-linear part, okay, and this was anyway your T P I J T. So, you have this expression and then you have this expression. Okay. Now, you notice that, okay, so let me rub this. If you notice this term over here, this has a delta P here, it has delta eta here. So, product of two very small quantities gives you an even smaller quantity. So, we can just simply neglect this. Okay. So, this is what we do, we are doing as linearization, we are neglecting the higher order terms. Okay. And then we can use the following approximation. So, this is the approximation that Bathe uses, that T delta P I j is equal to C I j K L E P delta epsilon K L minus the thermal part plus R. Okay. So, with this and neglecting what I said was the higher order terms, you will get the following, okay, simplified and linearized governing equation. Okay. So, this equation when solved will yield only an approximate displacement, velocity, acceleration, strain, strain rate, stress and thermal stress field. Okay. So, everything is inbuilt here. Okay. So, this R contains the effect of temperature, okay, and strain rate. This Cij KL EP has the effect of hardening, it has the effect of temperature, it has the effect of strain rate. So, everything is here inside this equation. Okay. And if you directly solve it, you will get only an approximate solution which is not accurate. So, this approximate quantities are denoted by right superscript 1 here. Okay. So, if you do this, okay, you will write like this, the error. Okay. So, this is the right hand side. If you take everything on the left hand side, then the difference of the right hand side and whatever is there on the left hand side gives you the error, and this error has to be minimized using a Newton-Raphson iterative procedure. Okay. So, this is what we call residual. Okay. Remember, we had this residual in the solution procedure which we discussed in the previous lectures. Okay. So, now we have to solve this, okay, and you have to minimize this residual, so that the external forces balance out the internal forces, that is the internal forces and the inertia forces which are generated because of the externally applied forces, okay, body forces, surface traction and contact forces. Okay. So, now the linearized and the simplified governing equation which is given by equation 63 contains volume and surface integrals and cannot be solved analytically for most physical problems. Okay. So, what we do in most cases of interest, it may not be even possible to express the volume and surface mathematically. Okay. So, in case of, for example, impact problem, the body is deformed so much that you cannot even recognize that the initial body has, so say a cube would have become very deformed shape, okay, for example. So, this necessitates the use of a numerical method for the solution of governing equation, and we use the finite element method, okay, to approximate the field variables and the geometry. So, the field variable in our case is the displacement, and then the governing equation also contains the time derivative of the field variable, that is u, because we have an acceleration there. Therefore, the discretization in time we carry out using a finite difference scheme, which in our case will be the Newmark's time integration scheme. Okay. So, first we do the what is called the matrix notation. We define the matrix notation for the components of the linear and nonlinear part of the incremental Green-Lagrange strain tensor are represented by the following array form. Okay. So, you have the normal components of the incremental strain and you have the shear component. Okay. Similarly, delta eta is written like this. Okay. So, you will have as many terms as there are. Okay. So, you will have delta Vy, delta Vz, delta Wx, delta Wy and delta Wz. Okay. Now, the incremental thermal strain tensor can be written as following form, where the shear term are neglected. Okay. Our shear terms are anyway not neglected, it is equal to 0. So, there are only normal strains, thermal strains. The Cauchy stress using the Voigt notation we can write like this form, okay. And then the elastoplastic constitutive matrix, okay, and the vector r can be expressed in following form. Okay. So, this you can simplify yourself, this is what we write, okay. And this vector A is called the flow vector. If you read the theory of plasticity, you will come across this vector which is called the flow vector. It is normal to the yield surface, and this flow vector is given in the following form. It is a function of the divitoric part of the stresses divided by the equivalent stresses, okay, equivalent stress. And the remember equivalent stress is nothing but root over 3 by 2 sigma dash ij, sigma dash ij, or in direct notation we can write this as sigma dash double contracted with sigma dash. Okay. And the derivative of h is can be written like this, okay. And the linear elastic constitutive matrix CE is written in the following form. Remember, we have 2 here to take into account that 2 that we have in the strain, in the shear part of the strain. Okay. So, now if you substitute all those expressions 66 to 73 which we have in the previous slide in equation number 63, then you will get the following form. Okay. So, the integral form of the equation of motion can be written in the matrix form. So, this is the integral form of the equation of motion in the matrix form. Okay. So, this is the matrix form where, okay, so you have this inertia term over here, okay, and then you have this is the coupled term because of temperature and the mechanical field. Okay. So, this is the purely this is the thermal and mechanical also, this is thermal, okay, and this is the purely thermal field, okay. And then you have this matrix T here, and this matrix T has this following form, and this matrix R has this form, okay, where sigma which you see here is nothing but the stress tensor in the full 3/3 form, and this S contains the tensor R in full 3/3 form. Okay. Now, to do the finite element discretization of our equation number 74. Now, we can do the finite element discretization. We have everything in the matrix vector form. Okay. So, what we do? So, first we discretize our domain into number of finite elements, and then the incremental displacement field is approximated over each element E using following form, okay, where this here over here phi over here is nothing but the shape function matrix, okay, and delta U E is nothing but the elemental incremental displacement vector, that is the incremental displacement vector of node 1, then incremental displacement vector of node 2 all the way up to the number of nodes that will have. Okay. So, for example, for a 8 noded element, delta U E will be a 24 cross 1 matrix, okay, and this also will be a 24 cross 1, and this is a 24 cross 1. Therefore, eventually you will have a this is a 3 cross 1 at any point inside. So, there will be 3 displacements. So, this will be a 3 cross 24 matrix, okay, and this matrix is nothing but composed of following subvectors, and these vectors when you write can be written in terms of the shape functions of the n nodes of the element. So, n 1 n 2 all the way up to you will have say 8 noded element. So, you will have till n 8. Okay. So, this will be 0 n 8 0, and this will be 0 0 n 8 like this. Okay. So, this will be 1 cross 24, this is 1 cross 24, this is 1 cross 24. Therefore, this will be 3 cross 24. Okay. So, 3 cross 24 here and 24 cross 1 gives you 3 cross 1, which is the displacement at any point inside the element. Okay. So, it will have 3 displacement x, y and z. Okay. So, that is what we have. Okay. Now, the acceleration can be written by taking the double derivative of the increment of the displacement, and then using the finite element discretization, the acceleration at any point inside the element can be written in terms of the shape function matrix times the acceleration at the nodes. Okay. And the discretized version of the linear and nonlinear incremental strain field is given by following form. Okay. So, delta epsilon E is like this, delta eta is like this, okay, where the strain displacement matrix BL, which is L here is for linear. So, B, the linear part of the strain displacement matrix has the following form, where phi 1, phi 2, phi 3 have been already described, and this nonlinear part of the strain displacement matrix has this following form. Okay. So, this again will be, so this actually is a 24 cross 1. Okay. So, you will get what is called the big matrix over here, and this is also a matrix. So, finally, you will get from incremental displacement you can compute the incremental strain, and from incremental displacement you can compute the nonlinear part of the incremental, that delta eta. Okay. So, now when you substitute equation number 79 together with this expressions 80 to 87 in equation number 74, if you do this, okay, you will get the elemental form. For each element you will get the Newton's second law, okay, and which is given here. So, mass into acceleration plus the tangent matrix K times the incremental displacement delta u plus the internal forces plus the external forces plus the external forces because of the thermal. So, thermal external forces, and then you will have what is called the effect of thermal forces on the stress fields. Okay. So, those three terms you will have. Okay. So, remember because this was already linearized, so we are not getting mass into acceleration equal to net external force, we also have this tangent matrix times the incremental displacement. Okay. So, our objective is to find out this delta u, okay, and if we know this delta u, then we can compute this also here. Okay. So, we will see how we remove this t plus delta t u dot u double dot also here. Here T m is nothing but your elemental mass matrix. Okay. This is like n transpose a rho n. Okay. This is the elemental tangent matrix. So, this has the linear part, the nonlinear part. So, this is the what we saw in our previous discussion. This was this K mat. Okay. So, this was K geometric, okay, the geometric stiffness, and this is the stiffness which comes because of the thermal effect. Okay. So, this is a linear part, this is B transpose C B. Okay. This is the geometric part, this is B n transpose T B n, okay, and this is the thermal part which is B n transpose R B n. Okay. And the right hand side force vectors. So, this is your elemental internal force vector, this is B transpose sigma. If you recognize this as the same expression that we discussed in our formulation for hyperelastic material. So, this is the thermal part, okay, and this is the coupled thermomechanical part, okay, of the external right hand side force vector. Now, you can do the assembly, okay, you can do the assembly over all the elements. Okay. So, now everything is at element E, and you can do the assembly over all the elements, and if you do this, okay, if you do the assembly over all the elements, this leads to the global system of nonlinear equation, okay, global system of equations given by m into u double dot, this is the inertia terms, mu double dot mass into acceleration plus the tangent matrix times K delta u plus delta f plus the internal forces at time t plus the external forces at time t plus delta t plus the thermal global external force due to thermal strain at time t, and this is the global external force due to the change in the plastic properties at time t because of the thermal effect. Okay. So, here delta u is the global incremental displacement vector, t plus delta t u double dot is the global acceleration vector at time t plus delta t, T m is a global mass matrix, T k is the global tangent matrix, T f is the global internal force vector, okay, and this is the global external force vector at time t plus delta t. This is nothing but the global external force vector due to thermal strain at time t, and as I told already that F m is nothing but the global external force vector due to the change in plastic properties at time t, okay, because of the temperature change our plastic properties are also changing, and also they are changing because of the severe plastic deformation. Okay. So, then this incorporates all such effects. Okay. So, equation 95 represents a coupled linear second order ODE. Okay. And now, what we have to do is to convert this coupled linear second order ODE into a system of algebraic equation. Okay. So, how do we do that? We have to now go for approximation in time, discretization in time. So, this equation 95 completes your discretization in space. Okay. So, you have completed your discretization in space. Now, you have to do the discretization in time, and for this you use what is called the finite difference in time. Okay. So, just to note that you can either do finite difference formulation in time, or you can also do. So, in the current discussion we are using the finite difference formulation, but you can also use the finite element formulation. Okay. So, finite element formulation will give you what is called the energy momentum schemes. Okay. So, these schemes will have some criteria where the energy and momentum of this process can be conserved if it is a conservative system, or it can be dispersed, dissipated at a particular rate. Okay. But this is a little difficult to understand and difficult to apply. Okay. So, if you wish, you can go and look into the literature. There are a lot of papers which are research which is available, starting from the work of Simo and Tarnow in 1992. Okay. So, you can see this paper and all the papers which are referring this. So, in this present discussion we use the finite difference in time. Okay. So, finite difference in time means we use the procedure where the derivative of the expressions in time are approximated using certain known quantities at or unknown quantities at the current or the previous step. Okay. So, in finite difference you have what is called the explicit schemes and we have the implicit schemes. Okay. So, implicit schemes means that you need to do what is called the Newton-Raphson iterative procedure. Explicit scheme on the other hand, you do not need the Newton-Raphson iterative procedure. Okay. So, explicit scheme are only conditionally stable, while the implicit schemes are, at least for linear problem, they are unconditionally stable, but for nonlinear problem they can be unstable, but however you can take a much larger time step. Okay. So, if you are doing some very high velocity impact kind of problem, then definitely we use explicit scheme, because there to find out the tangent matrix K. Okay. So, the tangent matrix K is a very tedious process. So, we do not want to do that, but for certain problems where we do not require we do not have strain rate at that level, okay, then we can use what is called the implicit scheme. But implicit schemes can be used even for impact kind of problem. It would be just like it will be accurate, okay, because you will be using Newton-Raphson anyway. So, here we use what is called the Newmark's method, and the approximation for which is given by Bathe, and the formulation also, the derivation is also given. So, here the velocity at time t plus delta t is approximated in terms of the velocity at time t, acceleration at time t, and the acceleration at time t plus delta t. Okay. So, using Taylor series expansion you can write this, and then the displacement at time t is written in terms of displacement at time t plus delta t is written in terms of displacement at time t, the velocity at time t, the acceleration at time t, and the acceleration at time t plus delta t. Again you can obtain this using Taylor series expansion. Okay. So, here A0, A1, A2, A3 okay, are some constant that will be used, which depend on this constant kappa and delta, and kappa and delta are called the Newmark's constant, and they take the value of 1 by 4 and 1 by 2 respectively, and these values are derived from the unconditional stability property for linear system. Okay. For non-linear system, you have to change this value according to a certain relation which is given in Bethe, where you can have certain amount of dissipation, numerical dissipation. Okay. So, now if you substitute equation number 97 and splitting your displacement at time t plus delta t like this, okay, you can write equation 95 in the following form. Okay. So, you can write the matrix KD times the incremental displacement plus A0 m into u plus f equal to the right hand side force vector, where A0 is here. Okay. So, this is A0. So, these quantities are at time t and therefore, they are known. The forces at time t plus delta t are usually known. Okay. External forces are known. Okay. And even this forces are at time t. So, we know that, and this KD is computed based at time t. Okay. So, that also we can compute. So, the only thing which cannot be known right now is delta u. Therefore, if you can solve equation 99, you will get your solution. Okay. So, the KD is nothing but A0 m plus k, and f t plus delta t f d is nothing but the external force plus m times this quantity over here. This is nothing but the acceleration, okay, approximation. Okay. Now, at time t you can write the forces like this. Okay. So, now if you use equation number 53, acceleration at time t, equation 101, you can write like this. Okay. If you write this at time t, you can write the following expression, and when you substitute for the expression of the acceleration at time t and the force, external force at time f, you can write this equation. Okay. And if you decompose the effective force vector, which is this here, as the effective force at time t plus the incremental effective force, we can write equation 9 as following form. Okay. Where this delta f t is given by the force at time, external force at time t minus the external force at time, external force at time t plus delta t minus the external force at time t, and this is what we have. Okay. So, this algebraic system of equation given by equation 105 is solved to obtain the incremental displacement. Okay. So, equation 5 is what you solve to get delta u. So, once you solve for incremental displacement delta u, okay, the velocity and acceleration at time t plus delta t can be obtained by equation number 97. Okay. And using the expressions 98 for the numeric constants, you can compute. Okay. So, you can get t plus delta t u as t u plus t delta u. Okay. So, this should be t delta u. So, you can get t plus delta t u, and using equation number 107, once you have t plus delta t u, you can find out the velocity, acceleration at t plus delta t u, t plus delta t, and once you have the acceleration at t plus delta t, you have displacement at t plus delta t, you can get the velocity as t plus delta t, where you will use the acceleration at t plus delta t. Okay. So, from equation 107 and 108, you can get the velocity and acceleration at t plus delta t. So, once you know the displacement and velocity and acceleration at time t plus delta t, you know everything. Okay. Now, this equation 105 has been obtained by linearizing and simplifying the system response about the dynamic equilibrium position at time t. Okay. So, this error in this linearization and simplification is expected to be small, provided the time steps are small enough. From the cost consideration viewpoint, one must endeavor to employ as large time step as possible. If the chosen time step is large, errors resulting from the linearization and simplification may not be negligible, and their accumulation may lead to gross error or instability of the solution. So, based on the accuracy consideration, iterative corrections to minimize the error of the solution of the linearized and simplified system of equation given by equation 5 are desirable at all time steps. Okay. So, what we do? We have to set up the Newton-Raphson iterative procedure, and we set up the Newton-Raphson iterative procedure like this. Okay. So, the K effective tangent matrix evaluated at I minus 1, okay, and this is for approximation for t plus delta t, times the incremental displacement vector for iteration I is equal to the residual force vector corresponding to iteration I minus 1. Okay. So, this delta Fu at I minus 1 is given by following form. Okay. So, this is the external force, this contains the external traction plus the contact force. So, this is the body forces at I minus 1 and this is the mass into acceleration at I minus 1. So, for the first iteration we have the equation 109 can be written like this, where the coefficient matrix, okay, or the tangent matrix is approximated by this here, and the unbalanced force vector or the residual vector is approximated by following expression. Okay. So, you can solve this equation 109, okay, iteratively over a particular time increment going from t to t plus delta t, and you can get the value of delta u. Okay. So, here the displacements are updated, okay, in a incremental manner rather than iterative manner. We update the displacement in a incremental manner. Okay. Now, our convergence criteria that we use, so we had discussed 3 types of convergence criteria. So, we use the residual of the unbalanced force vector divided by the norm of the external force vector at time I, and if this is less than the specified tolerance, that is the tolerance maybe this is what the user will give, we can get the solution. Okay. Not always, but in the correct setting you will get the solution. Okay. Now, how do you determine the stresses once you have determined? Okay. So, once you have determined this delta u, what you do? So, your delta u t will be summation I goes from 1, okay, I goes from 1 to say n is the number of Newton-Raphson steps that you do, will be d delta u I. Okay. So, at the end of ith iteration you will have, okay, you will have the incremental displacement. Now, from this incremental displacement, how do you find out the stresses? Okay. So, this is what you do once you have found out the displacement. So, determination of the steps is carried out using the following procedure. Okay. So, the evaluation of stress component at the Gauss points of the element is done by the following stepwise procedure. Remember, we are using a different kind of objective stress rate. Okay. So, we calculate the matrix of incremental deformation gradient tensor F with respect to the fixed frame given by equation number 22, and we use the following formula. And it should be noted that the position vector x corresponds to the equilibrium position. Okay. Now, we decompose the matrix of the incremental deformation gradient tensor using right polar decomposition into an orthogonal part and a symmetric part R and U using equation number 23. And from u square equal to, okay, so C is F transpose F, okay, and this is equal to u square. Okay. So, we do find out F and then we find out F transpose F to get us u square, and then from there we find out the principal stretches, okay, from equation number 24. And we also determine the matrix Q, the rows of which are contain the direction cosines of the eigenvectors of the right stretch tensor U. Okay. Then from the incremental displacement T delta U, we find out the incremental strain delta epsilon L, and this is the matrix of the incremental logarithmic strain tensor with respect to the material frame using equation number 27. And from this incremental logarithmic strain tensor, we find out the matrix of incremental Cauchy stress tensor with respect to the material frame using equation number 48. Okay. So, using equation number 28, we update the Cauchy stress tensor at time t plus delta t with respect to the fixed frame, and if the updated state of stress does not lie on the yield surface, we then have to use the radial backward return algorithm, which we are not discussing in this particular lecture, because itself is a big topic. So, once you find out that the updated state of stress does not lie on the yield surface, then we use the radial return backward radial return algorithm to bring these stresses back to the yield surface, and we correct it iteratively till the stresses lies on the yield surface. Okay. This is the consistency condition that we discuss. Now, this completes the procedure for finding out the stresses. Now, during the deformation, there can be what is called the local unloading. The Gauss point may experience unloading, the decrease in stresses or the forces, because of which it may go from plastic state to elastic state, which is called the unloading. Now, to detect that unloading, okay, what we have to do? We have to incorporate a particular procedure, and for this we have incorporated by using the unloading criteria, which is given by Chakravarti in his 1981, okay, sorry, this is 1981 book, where it is given by N transpose delta sigma should be less than 0. Here delta sigma is the incremental stress and N represent the unit outward normal to the yield surface. And remember, this is nothing but your flow vector that we had. Okay. Remember A, that was the flow vector. So, this N is nothing but the flow vector. So, the flow vector that we described is used here. Okay. And N represent the unit normal outward normal vector to the yield surface at the current stress points, sigma in the 9D stress space. Okay. Some of the other salient features that we have to use is, depending on the size of the problem, okay, if it is a very big problem, then we may like to go for modified Newton-Raphson procedure instead of the full Newton-Raphson, which means that the tangent matrix is not computed at each and every step. This also we have discussed in our discussion on Newton-Raphson method. Okay. And if the Newton-Raphson procedure experiences some kind of divergence, so we have to incorporate some line search method. Okay. So, we have to handle those divergence. For static problems, okay, we have to incorporate, and static problems which are dominated by where displacements are specified, not the forces, we have to use what is called the arc length method. And here in this formulation we use the arc length method proposed by Batos and Dutt in 1979. If you are solving a dynamic problem, then definitely depending on the convergence rate, you have to use what is called the adaptive time stepping, which means that the delta t can go up, it can go down depending on the rate at which your Newton-Raphson procedure is updated. So, if your Newton-Raphson procedure fails and the line search also fails, then the next step is to use the adaptive time stepping to maybe decrease the delta t and then redo the complete step from t to t plus delta t. Okay. And the last step, okay, the last salient feature that you have to use is to reduce the computational cost. Only the non-zero entries of the tangent matrix have to be stored. Remember, for a very big problem, your K matrix will be only containing up to 5 to 10% non-zero values. The 90% to 95% of the values will be 0. So, we do not have to store those values. So, what we do? We have to use what is called a static condensation scheme, and we just store only the non-zero values of the tangent matrix. For this, the code needs to be suitably modified. Okay. So, with this we have carried out the finite element finite difference discretization of the integral equation of motion. So, the next step is to do the thermal formulation and the contact formulation, and then we will look into some of the validation problem and the results, and after that we will conclude this lecture. Okay. So, with this I will end today's lecture. Okay. Thank you.